Hi, everybody. I'm going to go over a little introduction on acid-base reactions so that when we get started on them next week, you have a little bit of background that we can work with as we talk about it more. So hopefully this is kind of review. We're thinking about acids and bases, and kind of our goals here are we want to make sure that we are able to identify the most acidic proton in a molecule, as well as identify the most basic atom in a molecule. So this might seem kind of random right now, but one of the things we want to keep in mind is that, especially since I know that a lot of you are heading towards some kind of medical profession, we are always thinking about what reactions are going on in the body. And there are so many acid-base reactions that happen in our bodies, in biological systems. Acidity and what we'll be talking about on Thursday as pKa, they are all very, very important tools that we use to kind of think about what kinds of reactions are going on and what the environment looks like in certain biological systems. So we want to definitely be keeping in mind these acid-base problems. It is going to be pervasive throughout organic chemistry, again, just kind of like resonance, and it actually uses a lot of resonance, which we'll see. So just to get started talking about acids and bases, we want to kind of think about what the generic acid and base reactions look like. So if I have some generic acid, I'm generally looking for something that has protons, okay? And we want to remember a proton is just H plus, right? So no electrons. Okay, you're going to identify them as hydrogens, right? So if we look at a molecule, when we draw in all the hydrogens like we've been practicing, those are our protons that we're after. So organic chemists often don't call them hydrogens, we call them protons, because that's often how we use them, is just an H plus with no electrons attached. So we have some sort of acid that has hydrogens on it or protons on it. And then we have some kind of base. So that's what we're using here. So this is going to be our acid. This is going to be our base. So the acid-base reaction that happens is the base has to have something that has lone pairs on it, okay? So the base has to have the electrons to start the whole process. So in this case, we're using oxygen, which has 2 lone pairs on it. So the lone pairs on that oxygen are going to go and attack our proton. We'll use kind of like, it seems rather harsh words, but we're going to have the oxygen lone pair go attack that proton. That arrow that I just drew is going to make a sigma bond between O and H, okay? So we obviously know that H can't have more than one bond. So the bond between H and A has to break. Okay, and notice that the arrows that I'm using here are exactly the same as our resonance arrows, except we're not using pi bonds this time, right? We're making sigma bonds and we're breaking sigma bonds. So in the 2 arrows that I have drawn here, I make a sigma, break a sigma. So when we're doing this, the electrons that are shared between the hydrogen and the other part of the molecule, so in this case A, those 2 electrons in that bond both end up on A, and that's what we see over here. Okay, so that lone pair on A used to be that old sigma bond. And then we have H3O plus now, because now we have an extra proton on our water, so now it's H3O plus, and that oxygen is now positively charged, okay? But all of the electrons in the new OH bond that we have came from the oxygen itself, that oxygen lone pair. So once we do our acid-base reaction, we're left with that A minus and the H3O plus. That A minus is what we call our conjugate base. Okay, and our H3O plus is our conjugate acid. And all it means is that if you look at it from the right-hand side, H3O plus would be your acid going that direction. A minus is your base going that direction, okay? So just, that's kind of the nomenclature that we're going to be using. We're going to see it come up a lot. So we got to get used to using that new vocabulary. So if we start off with bases, we have pretty much the exact same situation going on. So if I have some sort of generic base, again, note, I need to have something with lone pairs. So this is going to be my base. And in this case, I'm going to use water as my acid. So remember back in Gen Chem, water can be an acid or a base depending on the conditions. So same thing happens here. We're going to use the lone pair from the base. We're going to go grab a proton, and then the electrons that are shared, in this case between O and H, those are going to end up on our oxygen. So again, this tail is showing that we're taking those 2 electrons and putting them onto our oxygen. And then that gives us a conjugate acid over here and a conjugate base. Okay, so once we have those, let's think about what it'll look like for organic chemistry. So let's look at some organic acids and organic bases. Oops. Okay, so if I have an organic acid, a really good example of that is acetic acid. Okay, so this is acetic acid. This is actually the component in vinegar that makes it vinegar. So it's pretty much this molecule in water is what we use as vinegar. So acetic acid, it kind of has that, you can use it to dissolve hard water and all that kind of stuff. Also tangy. Acids are often labeled as like sour or tangy or something. Back when people used to taste things in the lab, but please don't taste things in the lab. So if I have that acetic acid, that functional group here is actually a carboxylic acid, which we will be talking about later. So that's a pretty common organic acid. For organic bases, one really common one is triethylamine. Okay, so I have triethylamine here. We just have that nitrogen with the lone pair on it. So again, we're looking at things that have a lone pair. So let's look at what they look like when we actually start to do reactions with them. So if I'm just going to compare this to another molecule. So we're going to compare this to ethanol, okay? So this is the molecule that is what you think of as alcohol, like alcoholic beverages, that's ethanol. So if I have these 2 molecules, we're going to compare those 2 to see which one is more acidic and why acetic acid in particular is pretty acidic. So I'm going to react both of these with water. Okay, so water is going to be our base in both cases. So we're going to have the lone pair on our oxygen. We're going to go grab that proton, and electrons move onto the oxygen. Okay, so that's going to give us that conjugate base. Okay, so remember we have acid goes to our conjugate base. And then we have the other side, same thing. And we're going to go grab that proton. Electrons move onto the oxygen. We get that conjugate base. And in both cases, we're going to form H3O plus. And that's our conjugate acid, okay? So if we're looking at these 2, what's really the difference here? We have, I'm actually going to move the H3O plus up so that I can Okay, so I have one that has an O- next to an sp3 carbon, one that has an O- next to an sp2 carbon. So whenever we do this, we should be thinking to ourselves, can I draw resonance structures, which is what we just learned. So hopefully we can see that we can do this type of resonance structure. And let me draw on some more pairs. So I can have the negative charge delocalize. So that we have that. If I was to draw a resonance hybrid, right, we know that we have charge delocalized between those two oxygens. They are both delta minus. So we have a hybrid that looks like that. So on the other side, so this, let me just write this down real quick. So this one is delocalized. Okay, so we know that we have a delocalized charge. Delocalization equals more stable, lower energy. So for the other side, because I have the two H's there, that charge is localized. Okay, so I have a localized charge in that system. So between the two of them, I have negative charges on oxygen, so that is kind of the same, but I can delocalize it over two oxygens in the acetic acid case. So this one is more acidic. Okay, because, and this is a really important idea here. So the stronger acid makes the more stable conjugate base. Okay, so the stronger the acid, the more stable the conjugate base is going to be. And we're going to read more stable as lower energy. Okay, so lower energy conjugate base. So if we're looking at this, that delocalized charge is more stable. And this acetic acid is more acidic. You can also read that as more reactive. Okay, whereas the ethanol, the one on the left, this is less reactive, leading to a more reactive conjugate base. Okay, that conjugate base is actually used as a fairly good base. So we will see bases like that used later in the semester. Whereas this conjugate base is a very, very weak base, and you wouldn't normally use it for much besides possibly buffering something, but it's a pretty weak base in terms of the whole scale of things. So we saw how resonance could be really important. There are other factors that determine acidity or basicity. So let's go back to our organic base example. And let's compare this to water. Okay, so we're going to compare triethylamine to water. Okay, so I have H2O with 2 lone pairs, triethylamine with 1 lone pair. So I'm going to react both of these with water, and we'll look at some acid-base reactions with those. And it's going to be a little bit weird to look at an acid-base reaction between water itself, but this is actually something that happens a lot. Water is always going to have a little bit of equilibrium between the H2O and then the 2 component pieces, which are the H3O plus and the OH minus. So we always have a little bit of that around whenever we have water. So we're going to use the base we're going to attack the acid. Okay, so we start from the electrons of the base. We go grab a proton. We're going to form that sigma bond. And then we break that sigma bond to put electrons onto the oxygen. So that's going to give us that conjugate acid. Okay, so remember we've got base. This is our conjugate acid. We also are going to have OH minus. Okay, and then for the water side, same exact thing. We're going to take the lone pairs of the oxygen, form a new sigma bond to H, break that OH bond, and put it onto the oxygen. So then that's going to give us H3O plus OH minus. Okay, so, and we've got our conjugate acid here. All right, so if we compare these two this time, so do we, number one question, do we have any resonance going on here? No, right? Because we don't have any pi bonds nearby. We don't have anything to do resonance with. So these are both localized charges. Okay, they can't go anywhere. So then we have to find a different way to compare them and see which one is more basic and why. So if we look at this, if we're comparing where the charges are, so nitrogen versus oxygen, we know that nitrogen is less electronegative than oxygen. So it's going to be more stable with a positive charge than oxygen. Okay, whereas oxygen is more electronegative. So that's going to be less stable with a positive charge. Okay, so this is more basic. This is less basic, leading this conjugate acid to be more stable and this one to be more reactive. Okay, so if we're comparing the two acids, this is a stronger acid than this is because that oxygen more desperately wants to get rid of the H plus so that it can go back to being neutral oxygen again. Okay, so just like in the acid case, the stronger base makes the more stable. And again, we're going to think about this as lower energy. Well, that W really got away from me. Conjugate acid. Okay, so in both of these cases, it's much, much easier to look at the conjugate base or the conjugate acid than looking at the original structure. Okay, and one of the things that you can think about with that is think about how difficult we found it to draw resonance structures for neutral molecules, but how it was much easier to look at them when they were charged. Okay, same thing here. It's a lot easier to compare charged systems to see who can balance out that charge better than it is to try to compare neutral systems where, I mean, maybe one is better than the other, but it's really hard to tell with neutral molecules. So always draw out the conjugate base, the conjugate acid, depending on the problem that you're doing. But don't just stay with the original acid or base that you're given. It's going to be way harder that way than if you just drew out the conjugate product. Okay, so hopefully this is gonna be a helpful little intro for what we're gonna talk about on Tuesday. And we will be discussing this for a little bit and using our newfound resonance skills along the way. So have a good day, everybody, and please ask questions and we will talk more about this.